right, everybody, let's do some graphing radical functions. The first thing you see here is the parent functions. We're going to focus on two of them. Any radical function could have a different index. Of course, the square root function has an index of 2. Cube root function has an index of 3. We're going to focus on these. Most of your even indexes will look similar to the square root. Your odd indexes will look similar to the cube root. Okay, so you want to have those graphed, you want to have the domain and range of that recorded. Notice you could write your domain and range in two different kinds of notation. So you can have inequality notation or interval notation over both of them. Oh goodness, I forgot a parenthesis on that one. There we go. So take a minute, press pause, be sure you have this information. We have all of our transformations here. The things that you want to look for with transformations is what happens around the radical. So in the past, it's been what happens in parentheses. In this particular set of functions, it's going to be what happens in the radical. So your right and left movements actually happen under the radical, whereas up and down will happen outside of the radical. A reflection in the y is in the radical, a reflection in the x is outside the radical, and so on and so forth. Your horizontal stretch and shrink are inside the radical, your vertical stretch and shrink are outside the radical. So everything, all of your transformations are in relation to the radical. So let's do some practice problems. Okay, first thing you want to do here, we have example 1. We're going to graph each function and identify the domain and range. Now, in order to do that, I do need the parent function graphed. So the parent function of this right here is going to be the square root function. Notice this is the square root of 1/4 of x. So the parent function is going to be y equals the square root of x. So that's what you need to have graphed. So just press pause and get that parent function on your graph. So once I have that parent function here, I can start to deal with these transformations. So this 1/4 right here happening underneath the radical and right in front of the x, that's going to be a horizontal stretch. Notice that it's 1/4, a number between 0 and 1. So since that is a horizontal stretch, that's going to be a horizontal stretch. I'm going to write this down here. A horizontal stretch by a factor of 4. You may ask where I got that information. Well, I see that I have a number between 0 and 1 right in front of x. So on my table here, when that happened, it actually happened with 1/2, it said it was a horizontal stretch by a factor of 2, the reciprocal of 1/2. So in this case, it would be the reciprocal of 1/4. Now that's important to me because it tells me what I need to change in my table. So in my original parent function table, right, I had 0, 0, 1, 1, 4, 2, and 9, 3. Now that I have a horizontal stretch, I'm going to have to make changes to the horizontal, all right? So that means my y values will stay the same. I don't need to change those, but the horizontal will be stretched by a factor of 4. Factor means multiply. So I'm going to take every one of these, I'm going to multiply it by 4. All right, so 0 times 4 is 0, 1 times 4 is 4, 4 times 4 is 16, 9 times 4 is 36. And then I'm going to put each of these points onto my graph. So I have 0, 0, 4, 1, 16, 2 is going to be off the graph. So we're just going to go as far as we can. And this is going to be the graph of f. So you can see here that's going to be a horizontal stretch because I'm grabbing this by the sides and stretching horizontally. So that's why it looks leaner, looks a little bit closer to the x-axis. The domain, notice the domain of my, am I on the screen? Okay, notice the domain of f. Okay, it's still starting at 0 and going to infinity. And the range is also starting at 0 and going to infinity. And that's super interesting because that matches the domain and range of the parent function. So that's pretty neat. Here, again, in order to graph this, I do need to recognize what the parent function is. I see that I have a radical and an index of 3. So my parent function in this case would be the third root of x, and that is the graph I would need. So go ahead and press pause and put that parent function on your graph. There we are. And remember, the transformations are going to tell me what I need to do to make this new graph, the new g of x graph. So for g of x, the first thing I see is a negative right after the equal sign. So whenever I start my function with a negative right after the equal sign, I know that I have a reflection. So because this reflection is outside of the radical, it's going to be a reflection in the x-axis. Also, I have a 3 outside of the radical and right in the front. A 3 is bigger than 1. So since it's in the front, it's not in the radical. That means it's a vertical stretch or compress. 3 is bigger than 1, so it's a vertical stretch. So that's going to be a vertical stretch by a factor of 3. So now when I make a table for g of x, I need to reflect my x-axis, so all of my x's should be reflected. So now I'm going to start with the positives and lead down to the negatives over here. So notice I just took these and reflected them. And then vertical stretch, vertical means I'm changing the y values and I'm multiplying factor of 3. So negative 2 times 3 is negative 6, negative 1 times 3 is negative 3, 0 times 3 is 0, 1 times 3 is 3, and 2 times 3 is 6. And these are my new points. I can plot these new points on my graph and see my new function. So take a minute and do that. And once you have that graphed here, you might want to label that. And we're going to find the domain and range of our new g function. Now you can see that it's been reflected over the x, you can see that, and we've had a vertical stretch. So we've grabbed our function and stretched it vertically. That's why these arrows are coming out much, much farther up and down than our originals did. So that domain, notice we go all the way to the left forever and all the way to the right forever. The range goes down forever and up forever. Very, very similar to the parent function. In fact, the exact same domain and range as the parent function. So, very neat. Okay, so we just need to describe the transformations and then graph them, similar to what we did before. So go ahead and take a minute, press pause and get your parent functions. We're very lucky because they tell us the parent function on these. Our parent function right here is the square root of x, and the parent function here is a cube root of x. So press pause and graph your parent functions. Okay, so I have my parent functions graphed here. So here, g of x, let's look at these transformations. So the minus 3 is happening under the radical. Things that happen under the radical will be horizontal. In this case, it is still a translation or a slide. And since it's negative 3, it's going to be to the right. So the parentheses and the radical are going to be doing that same job that transformations have been doing all along. So this is a horizontal translation or a slide. Right 3 units. And the way I knew that was this minus 3 under the radical right there. And then this plus 4 that is not under the radical, it's on the very, very end, but not in a radical, that's going to be a vertical translation up 4 units. So all I have to do to graph this, it's really simple since this is just a slide, is I have to take every point and I want to move those points right 3 and up 4. So I'm going to take all of these points and go right 3 up 4. So I'm going to start at 0, 0, 1, 2, 3, 1, 2, 3, 4. I'm going to do 1, 1, 1, 2, 3, 1, 2, 3, 4. I'm looking at the point 4, 2. 1, 2, 3, 1, 2, 3, 4. I don't think I can make that one go over 3 steps. and then we're just going to graph it from there. So that's going to be my g of x. Notice that these will have a different domain. The domain from here is 0 to infinity. The domain here is going to be 3 to infinity. So a translation will change your domain for the square root function. All right. Now over here, let's look at this. I'm going to change colors because I'm on the other side of the paper there. I notice that I have a negative, but that negative is under the radical. Negatives are still a reflection, but since this is under the radical, this is going to be a reflection in the y-axis. All right. I have an 8 in front of my variable. However, that 8 is under the radical. So that is going to be a horizontal stretch or compress. In this case, because 8 is bigger than 1, it's going to be a horizontal shrink. Excuse me, we say shrink in this class, not compress. My bad. Shrink by a factor of 1 over 8. So that is different. Remember, when you're doing a horizontal stretch or a shrink, you use a factor that is the reciprocal of the number that's in the radical, okay, or in the equation. So that being said, now my original graph, if you remember how we did that, we had -8, -1, 0, 1, and 8. -2, -1, 0, 1, 2. Now I need a table for my new function. So my new function g of x. First thing I want to do is reflect the y-axis. So this is the y-axis, the y, so I'm going to reflect them. So I have 2, 1, 0, -1, -2. Then I need a horizontal shrink by a factor of 1 over 8. So I'm going to take each of these horizontal measures, which is x, and multiply them by 1 over 8. So -8 times 1 over 8 is -1 over 8. -1 times 1 over 8, 0 times 1 over 8, 1 times 1 over 8, ooh, that should have been negative, this should be a 1. That should be a 1. -8 times 1 over 8 is -1. That's a -1. Woo, math. There we go. And I'm going to graph that on my paper. And you can see, after you've graphed it, you can see that horizontal shrink. You can see that we're pressing that in horizontally, which is making this a little bit more up and down. It's that horizontal shrink. It's the pressing in. And then the reflection, of course, over the y-axis is clear when you graph that as well. Now let's look at writing an equation. So writing an equation can be a little bit more challenging, so let's look at the information that they've given us. Okay, so let the graph of G be a horizontal shrink by a factor of 1/6, there's one transformation, followed by a translation 3 units to the left, and the original of the graph of this guy right here. So the parent function was f of x equals the cube root of x. So we know our index is going to be 3. So we're going to write a rule for g of x. Now, in order to have this horizontal shrink by a factor of 1/6, I know that a horizontal stretch or compress happens under the radical, and it's going to be the reciprocal of 1/6 in the equation. So it's going to be a 6 in the equation. Then I have to go left 3. Now remember, when you go left, you actually add. So I have an x plus 3 under the radical. That way I go to the left, not up. Okay? And I do want to put that in parentheses. I want to make sure that my left transformation is separate from the horizontal stretch or shrink. You can simplify that. If you simplify that, you would just distribute that 6 through and have 6x plus 18. And that's why it's really important to go ahead and use these parentheses, because when you don't, obviously it gets confusing how much you went to the left. So you can use this information to graph all kinds of things. In the event that you have something like y to the power of 2, and what I want to do, I've already worked this out, I kind of just want to talk you through it really quickly. So let's say I want to graph something like 1/2 y squared equals x. Okay, so what we're doing is we're squaring the y instead of squaring the x. Squaring the x is what we normally do. Now, in order to do this, I do need this to be in y equals to graph it. So what I would do is multiply both sides by 2. That way I'm isolating this y squared. To undo y squared, I would take the square root. This is an equation, so I would do that to both sides. I'm taking the square root. My index is 2, so my answer has to be positive or negative. Square root property says that. So y equals positive or negative square root of 2x. So what you do is you actually have two options. Your first option, y1, is that y equals the positive square root of 2x. Your second option, y2, is that y equals the negative square root of 2x. You would make a table and then plot your points. And what's going to happen is this will be your positive option right here. And then this side will be your negative option here reflected over the x-axis. So you can see that this is reflected over the x-axis by putting that negative in the front. This is a great way to graph circles as well, so let's look at that option. In the event that you wanted to graph a circle, like x squared plus y squared equals 16, if you remember, circles are x squared plus y squared equal r squared. So we know our radius is going to be 4. But nonetheless, what you would do, first I need to isolate y squared. I would subtract x squared from both sides, leaving me with y squared equals 16 minus x squared. I would then take the square root of both sides, and y would be positive or negative square root of 16 minus x squared. I would make a table for my two options. My first option being the positive square root of 16 minus x squared. My second option being the negative square root of 16 minus x squared. I would make my table. My positive option would be above the x-axis, and my negative option would be below the x-axis. This is not the best circle I have ever graphed, but alas, it's supposed to be a circle, and that's how you graph circles essentially, is you graph the top and then you graph the bottom. So, and that's how you would put circles on a Cartesian plane. So, extra fun, interesting information for you there.